Good afternoon. I'm Steve Widdicombe from Plymouth Marine Laboratory. Sorry I can't be with you this afternoon, but I'd like to thank the organisers for giving me the opportunity to present you my work through this short presentation. Today I'll be talking to you about establishing effective environmental baselines for offshore CCS. But before I do, I just want to remind everyone that the purpose of doing CCS is primarily to make a practical and significant contribution to reducing atmospheric CO2 emissions. So in essence, what we're trying to do is something that's inherently beneficial to the marine environment. But before we do undertake any new activity in the marine environment, it's essential that we ensure that we are not creating any harm or damage to the ecosystem that we're initially setting out to try and protect or conserve. So in order to do that, we need to make sure we can assess any environmental risks associated with the activity we're undertaking. We need to be able to design ways of effectively monitoring for changes or impacts that might be associated with the activity in which we're undertaking. And we also need to be able to determine the extent of any environmental damage that is caused by something we do in the course of the activity that we're engaged with. Primarily, this is to reassure ourselves and also others that we can actually conduct CCS in an environmentally safe and responsible way. So back to baselines. How do you go about building an effective environmental baseline specifically for CCS? And that is one of the key questions we're looking to address within the EU-funded project STEMM-CCS. But before I go on to answer this question, I would just like to say thank you to one of the partners within the project, Shell, who have given us the opportunity to test some of the ideas that we generate within our project in a real-world situation here in the northern North Sea at the Goldeneye platform and the Goldeneye field. So the first thing we realised when we considered the problems associated with CCS environmental baselines were that they provided different challenges to those baselines we'd considered before, mainly due to the large spatial extent over which geological complexes exist, the places where CO2 is going to be stored, the fact that we want to store CO2 permanently rather than just being a short period of activity of a few weeks or a few months, and also the fact that carbon dioxide is a natural element within the marine environment, so it already interacts with biological processes and organisms in a way in which we need to understand so we can differentiate those normal changes with those that might be associated with any activity that we're undertaking through CCS. In order to structure the way in which we wanted to go about constructing the baseline, we decided to create a methodological framework in which we could consider a few key activities that we felt were important to undertake in order to get to this cost-effective environmental baseline. One of those was site characterization. This is in essence describing the environment in which the activity is taking place. The second is being able to target the sampling that we do to ensure that we don't spend too many resources or too much time and effort sampling in the wrong places or taking the wrong samples. And the final thing is a hindcast baseline reconstruction, which in essence means, can we gain information on how the system has been in the past, even when we haven't got samples available that have been taken in the past? When it comes to targeting sampling and data collection effectively, it's important not to just go ahead and collect as much data as you can from as many different places as you can. All the data sampling and data gathering must be done in a targeted and a focused way. And the best way of organising that is to understand the scale at which you want to collect your data and the detail in which that data needs to be. And because CCS covers large temporal and spatial scales and a complex system which can require a lot of information in order to fully describe it, we've tried to allocate certain activities and data collection activities into a series of 4 tiers. And those tiers range from broad scale sampling, which we hope to be able to achieve with as minimal amount of effort as possible, tier 1, to the very focused intensive studies that look at very small areas but in a great deal of detail, and those are tier 4. So that in essence encapsulates what we're endeavouring to do in that central box, We want survey designs and survey techniques that allow us to play off data collection effort against the scale over which we're trying to collect it. When people think of impacts from CCS, the first thing you think of is the sea floor, and naturally so. If CO2 is to seep from geological storage, this will be the first interaction the CO2 has with the marine environment. So we need to know what organisms and habitats can be affected, and the area, as we've already discussed, associated with CCS activities could be very large. So how do we go about collecting enough information on the benthic or seafloor habitats that will allow us to understand the likely impacts of CCS? The tool we decided to look at was acoustic surveys, so in essence echo sounders. Now these have been used for many, many years, and they are often used to collect data on how deep the water is, but they can be used for so much more. We know that the data you receive back from an echo sounder survey also can tell us information about how hard or soft the seafloor is, and also how rough or smooth it is. And with this information, we can make predictions on what the seabed habitat is actually like and what animals are likely to live there. In addition, because echo sounder technology is certainly not new, there are quite a few existing data sets out there that we can reanalyze to give us this kind of information when we're looking to establish CCS in new areas. And this is what we have actually done in the Goldeneye area. This is a habitat map constructed from echo sounder data, which shows the way in which the different habitats from muddy sand through to sandy mud are distributed over the whole area. We can also use the data to identify features that exist on the seafloor, such as these pot marks, these blue dots on this image here. Features that might well have an influence over the type of community that live there. And then we can superimpose additional data that might be of interest to us, such as the intensity or the location of fishing pressure, which can change seabed communities and affect the communities that we're looking to study. So acoustic surveys could prove a powerful tool in being able to map large areas of seafloor for relatively little effort or expense. But what about the overlying water column? Do we need to ignore that because we feel that most of the impacts are on the seafloor? Well, no, we don't. The phytoplankton, these single-celled algae that live in the water, provide most of the food that the seabed requires in order to function. But the supply of this food isn't the same all the way through the year. And this variability in supply throughout the year also causes changes on the seafloor. So understanding how the phytoplankton community changes means we can start to understand how the benthos or the seafloor communities change. Not only does phytoplankton communities change throughout the year, through the seasons, they also change from year to year. And here we can see a long-term time series of phytoplankton biomass over a large number of years, showing that not every year is the same. So we need to be sure that we understand how phytoplankton communities are likely to change throughout the year and between years. Finally, in terms of the importance of phytoplankton, we also know that these single-celled algae interact strongly with the carbon dioxide and the carbonate chemistry system as they use the CO2 for photosynthesis. So as you see patterns in the phytoplankton community, you also see very strong related patterns in the carbonate chemistry parameters of the seawater, which means if you want to understand carbonate chemistry and use it as a tool for monitoring CCS, you also need to understand how the plankton are influencing this. So how do we measure phytoplankton communities over large spatial and temporal scales? Well, fortunately, phytoplankton contain coloured substances, coloured pigments, which they use for photosynthesis. And we can measure these pigments from space over huge geographical scales. And here we can see maps of chlorophyll mapped from space. And by combining those with other measurements that we can make, such as the availability of light and the temperature of the water, we can calculate primary production rates for pretty much any part of the planet. We also have long time series of these data. This particular image here shows the whole Pacific Ocean, over 19 years of integrated data that show us the average kind of productivity we'd expect in different parts of this whole ocean basin. But more relevant to CCS, we can see at regional scales how from month to month to month the satellite data can show us how these spring blooms evolve and where they're located. We've used this technology at the Goldeneye site, where we've looked at 9 different areas spread across the Goldeneye field. And even in this relatively small area, we can see that the phytoplankton blooms to the west of Goldeneye are very different to those on the east. Not only do they differ in terms of their seasonal patterns, they also differ in terms of their patterns from year to year to year. And we can even look at long-term trends and see that to the west of Goldeneye, productivity is increasing, and to the east it's decreasing. In addition to this, the new products are appearing from satellite-derived data, which could be extremely relevant to CCS activities. And these include measurements of carbon, CO2 fluxes, and even ocean pH. So remote sensing is another valuable tool to allow us to characterize areas, but also due to the huge wealth of existing data, we can recreate baselines which stretch back many years. The third and final tool that I'd like to introduce to you today are ecosystem models. And a large number of good ecosystem models already exist and are ready for us to use in CCS activities. These models expand upon observational data, and they allow us to create continuous baselines through space and time in areas where we only have sporadic observational data. They also give us the opportunity to provide information on those hard to measure parameters that can only be deducted from interactions with other parameters. Now, I'm not going to go into too much detail about how these specific models work, and I'd like to direct you towards Jerry Blackford's talk tomorrow morning. But what I would like to say and highlight is how powerful these models can be at moving information up and down through spatial and temporal scales. These models can be applied at global scales, down through regional scales, and down to local scales. And we can see that applied at the Goldeneye site, where we've taken these models and used them to look at processes that operate at the kilometre scale, all the way down to processes that can be operating at the metre scale. So immediately we have a tool which enables us to span across the kind of spatial and temporal variability that is essential for us to understand when we're dealing with CCS. So we add this third tool into our framework, and we can now start to see how by combining acoustic sampling, remote sampling from satellites, together with the ecosystem models which can synthesize understanding, we can begin to describe the wide areas that are likely to be of interest when it comes to the CCS activities. This will then also enable us to target our sampling in a much more cost-effective way and allow us also to recreate baselines in places where we haven't sampled before, so that we are not forced to delay the implementation of CCS until we have enough environmental data. So in summary, yes, constructing an effective environmental baseline for CCS is not without its challenges. This is largely due to the wide range of spatial and temporal scales that we need to consider, as well as the complex natural relationship CO2 has with the marine environment. But we do have some powerful tools we can already use to generate the data and understanding we need over all the appropriate scales. We even have access to virtual time machines that allow us to go back into the past as well as to forecast the future. In the next phase of the STEMM-CCS project, we will bring these tools together to create and test a comprehensive environmental baseline for the Goldeneye site, and thereby demonstrate that we do have the tools and the knowledge to implement CCS in an environmentally safe way. And with that, I'd like to say thank you to the European Commission for funding the STEMM-CCS project. I'd like to thank my co-authors, industrial partners and colleagues from across that project. I'd like to thank the organisers of GHGT 14 for allowing me to give this presentation virtually. And last but not least, I would like to thank you all for your attention. Sorry again I couldn't be with you here today, but I will be here tomorrow, and I'll be here at the meeting for the rest of the week and be very happy to answer any questions you may have. If you can't find me, please leave a message at the STEMM-CCS stand.